So the first step then is we have to determine the asymptotic behaviors. So let's go here with step 1. We're going to carry out an asymptotic analysis. And we really have two cases to consider. We have case 1, or case A, I guess I'll call it, right? Which is when R goes to 0. This is the more complicated case. The R goes to infinity case is actually a little bit quicker, so we'll do the harder one first. So as R goes to 0, we want to think about how our wave function rho is going to behave. Now, when we look at our equation, there are really two types of terms in this ODE. There is the second derivative term, and it has to balance all these other terms that have rhos in them. Now, when R heads towards 0, if I look at all of these rho terms, one of them very clearly dominates very strongly, and that is this first term. Right? So as R gets closer to 0, what I'm doing basically is I'm very closely balancing just these two terms. So I can set the sum of these two terms then actually equal to 0 because they are in approximate balance. So then what I'm looking at in this case is minus 1/2 rho double prime plus LL plus 1 over twice R squared times rho, and that must match up and give me 0. So therefore then, I can find the second derivative of rho, and it must then obey an equation like this, where it is some constants, L times L plus 1, right? Put this on the other side of the equation, the 2's go away, times then my function divided by R squared. So we want to think, what kind of functions might solve this type of an equation? This is a much simpler equation, so this is one of these we can do by inspection. So if we think about it, I want something I take that's a function of R, and I take two derivatives with respect to R, and what I get has just reduced the powers of R in my function by 2. Well, that sounds just like a monomial solution. So let's try monomials. I mean just a power, monomial. Try monomials. So I want to think that, rho of R is going to be something like, approximately in this limit, some constant times R to some power alpha. Now, we should check whether this works. The other thing to keep in mind is that if I want a fully general solution, notice I'm expecting that I need to find two linearly independent forms for my solution because it's a second order equation. So we will see what kind of solutions we can get out of this. So let's try that. Now, to try this, first I need to compute rho prime, the first derivative, which just brings down a factor of alpha. So I'll have alpha A times R to the alpha minus 1. Then the second derivative, rho double prime, will pull down another exponent, so that'd be alpha times alpha minus 1 times A to the R alpha minus 2. And what I need is that this must equal L times L plus 1 times rho over R squared. And rho is A, so times A, R to the alpha, that's rho, and then divide by R squared, R squared. So the first thing I hope you notice is that this has worked out nicely because this is R to the alpha minus 2, which is exactly the exponent that I find here. So we see that this actually works if, right, there's only certain powers of A that are going to work, powers A that will work, and I need alpha times alpha minus 1 here to match L times L plus 1. So that must equal L times L plus 1. Now, this, notice, is a nice quadratic equation, which is very good because I need to have two linearly independent solutions to make sure I found all the possible solutions. So there are two values of alpha that will work for this. And you can either solve it with the quadratic formula, or if we can solve it by inspection, and as long as we find two roots, we know we will have found all of the roots because it's quadratic. And you can actually stare at this a little bit, and by inspection, we can solve it. We have alpha could equal. One choice is, well, this is an integer times a neighboring integer, which is exactly what I have on the other side of my equation. So, in fact, if I pick alpha equals L plus 1, then I'll get L plus 1 times L, and that's what I started with. So that one works. The second solution looks something like this. Alpha equals, this one's a little trickier, but you'll see how I came by it. If I tell you that it's minus L, notice if I put minus L, then I'll have minus L times minus L minus 1. And by the time I cancel out all those minus signs, it's back to L times L plus 1. So I actually have two different possible solutions out here. So for rho, as r heads closer to 0, it's going to be, some amount of r to the first choice is L plus 1, plus some other amount b of r to the other value of to the other choice of alpha, r to the minus L. And this idea that I've got two linearly independent solutions out here should be something that we're kind of used to in these problems, right? We are used to the fact that we're over here, right? And we have to always be curving away from the axis. And all we found is that there are two different solutions. One of them goes to 0. That's r to the L plus 1. And the other possible solution out here, I'll just sketch it, also is always curving away from the axis, right? And that's r to the minus L. But that one blows up to infinity. So, like we usually have, there's a boundary condition we have to worry about to ensure that our functions are properly normalizable. And this first function doesn't seem to present any problem. It just goes to 0, so it's going to integrate to some nice number in here. It's the second part that heads up to infinity that could definitely cause us some trouble. So let's check on the normalization condition that we have. So let's check then the normalizability of this term of rho of r behaving something like r to the minus L. And of course, we're really hoping that this won't be normalizable, because after all, if it's not normalizable, then I actually have my solution as just this first piece. And that's typical for us when we apply boundary conditions in Schrodinger's equation on the far end of our interval. All right, so let's check the norm of that. So the norm of this, right, the normalizability that we are really checking is we're asking, can we actually integrate? Remember, we're really in 3 dimensions. Can we integrate over volume the square of my wave function? Now, the integral over volume in spherical coordinates is something like r squared dr, where r goes from 0 up to, infinity. And then I've got these other angular integrals, 0 to pi, sine theta d theta, integral d phi, from 0 to 2 pi. Now, psi we have to be a little bit careful about also, right? Psi, the psi's that we're looking at are products of our r's times our y-lm type angular portions. And r itself is related to rho, right? We've really made this a very effective equation, so we have to kind of remember all of our definitions. R is actually rho over, capital R is rho over little r. So this thing itself then is rho of little r divided by r times some, YLM, some angular functions. And I have to square those. So what I get then is something like rho squared of r divided by r squared times some magnitude YLM theta phi squared. Now, notice that I'm being a little bit cavalier about these angular portions and a little bit also about, modulo squared on rho. Rho seems to be real, so I could just write it as rho squared. I'm kind of cavalier about these angular integrals because my YLMs are all nice finite functions, right? And I'm integrating over finite angles. So none of these angular parts actually control whether or not this thing is normalizable or not. The key portion is going to be, and in fact, the YLMs are normalized, so those angular integrals will actually give me 1. But the key portions that I need to consider, the basic behavior I'm getting at, is I need to do an integral 0 to infinity dr. This r squared will cancel this r squared, right? And I'm left then with this rho of r quantity squared, which equals integral 0 to infinity. Now, for my r to the minus L solution, p squared is going to be something like, I'm integrating dr, b squared over r to the L squared, so r to the 2L. And this integral is undefined, right? If I have an integral dr over r squared, or r to the 4th, or r to the 6th, right, this will be actually an undefined value, and so it's not normalizable. Therefore, we can eliminate this term as violating our boundary conditions for normalizability, so it's not normalizable. Another quicker, more intuitive way, if you want to come to the same basic behavior and rule out these solutions, it's a little bit more intuitive, is to look at the diagram that I've given you, right? And to say, well, I need to have, some kind of finite value for my function over here, right? I want it to go to 0 because I'm about to hit a forbidden region. That's not, strictly speaking, 100% valid logic, but at least it helps us remember that we need the solutions here that actually go to 0. So that's our analysis then of case A.